Okay, this is where we left off last time, where I got spooked by teaching this one. It's really not that bad, but it is a little hairy. All right, so it's kind of tough to explain with words, so looking at the examples I think help, but here we go. You select two indices at random, kind of like a two-point crossover, in a similar way that we did like this one, the order crossover, right? So like in this example, I selected 3 and 7. Then I copy all the elements from 3 to 7. Often you don't include the last one, but it doesn't, whatever, implementation details, right? So 0, 1, 2, so over to there, okay? So far it's like the same as order crossover. Now, starting at the first selected index and value in the other parent, so that would be like here, the 8, or 0, 1, 2, 3, 8, okay? Copy non-copied elements to the child by find the index of the element that exists in the child in the non-copied parent. Okay, so here, the value of 8. Okay, we start with 8. Okay, then we go over and be like, oh, okay, well, there was a 4, right? So where's the 4 in this one? There. Okay, so put the 8 there. All right, so there, see? We go, okay, 8, oh, 8 goes to 4, 4, oh, there we go. Perfect, okay, cool. The value 4 exists at index 8, non-copied parent, thus the value of 8 is placed in index 8, okay? It is possible that the index the value should be copied to is already filled. So see like the value 2, so 2 to 5, but 5, it's already like there. So if that happens, you carry on. You go, oh, 7, so, okay, and then you put the 2 there. Okay, so you might have to do a bunch of bounces until you find like an available spot. And then, yeah, you copy the remaining elements in place. So this basically goes and finds where the, like let's think of the logic here. This will go and find where these can fit, like, oh, the 4, oh, okay, the 4 is already in there, right? So where that 4 from here could be, we could put the 8 because it's not in there yet. You know what? It doesn't matter. It doesn't matter. It's a hairy one. If you want to implement it, go for it.
There's logic to it.
There's logic. There's a method to the madness, but it's still madness, all right? But you could do it if you wanted. Don't. So, cycle crossover. This one's not too bad. Select an index at random. Identify the value at that index in parent 1. So let's say, well, okay, parent 1. Get the value at the selected index in parent 2. Find the index of that value in parent 1. Repeat until the whole cycle is found. So when the value at the original index in parent 1 is found in parent 2. Okay, yeah, so here. So here, it's saying like, okay, let's start at, okay, here. And we go, okay, well, 1, okay, 9. Oh, okay, where's the 9 in here? Okay, 9, great. And then, oh, where's the 4 in here? Oh, it's here. Okay, great, okay. And then where's the 8 here? Okay, it's here. And then, oh, there's the 1, and then we're back to here. So we found a cycle, okay? We found like, okay, there we go, cool. All right, so that's finding a cycle. And you're going to look for all cycles. So then we could start, okay, here, okay, 2 to 3. Well, where's the 3? Oh, there's the 3, and then 7. Oh, where's the 7? There's the 5. Okay, 2, 3. Oh, we found our cycle. Okay, so you identify all the cycles. And then here's like another cycle, right? But that one actually wouldn't change anything. All right, so result of applying cycle cross, okay, what do we mean? Okay, exchange the elements at the indices in the cycles. So because we know, like if you identify one cycle, we can swap them because I know that like, well, for every number in here, we've got the matching number here. So they're in different locations, but we can swap them and we'll still preserve the permutationness of it. Is that clear? Now you would just have to identify one. So I guess here we take that cycle and then just, oh, I guess we didn't do that one. We did Oh, okay, I guess we left the dark one, and we just did the copy of the 3, 7, 2, and 5. 3, 7, 2, 5. Da, 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 da. You see? Kind of neat, eh? So the trick with this one is if you find a cycle, all the elements in the cycle must have a matching number here, and then so we could swap them, and it won't destroy the permutation. Because I know this cycle has a 1, 4, 8, 9. 9, 8, 1, 4. The same numbers must be there if it's in the cycle, right? Pretty neat. I think it's cool. Right? And then mutation. So a swap mutation can work well. We talked about that one before. Pick two indices, swap them. A number of you said you did that for assignment 1. Then you have like insertion mutation. It's kind of similar, but you might pick two indices, but maybe you take the 5 out and like put it there and like smush them down a little bit. So you pick one and you decide where you're going to insert it to, and everyone kind of makes room, you see? Scramble mutation, pick some subset and shuffle that subset. Now you might look at this and be like, that's pretty destructive, right? Because you could almost think it's like swap mutation, maybe, I don't know. Like you could look at this, if we take this and we shuffle this in a different order, okay, cool. But also everything else that wasn't selected is left alone. So, you know, it's a little bit of both. Do you see the idea of scramble? Do like 2-point, kinda, like pick 2 points and then just shuffle where they are in there. And then inversion mutation. This is the one a lot of you did. Raise your hand if you did inversion mutation. One, yeah, a number of people did inversion mutation. This one makes sense for TSP. You know, kind of like reverse the path a little bit there. There's a lot of like, a lot of the path, like the adjacency is preserved, which is nice. There's only like 2 points where they'll be like really mixed up. Where if you go here, like, okay, all this will be left alone, but all of this will be mixed up. Like each from here to here to here to here to here. So there's more taking place. So it's kind of neat. And even like with swap mutation, like when you look here with the inversion, the only place where it gets mixed up is like here and here, right? At the edges. But with swap mutation, like if we go up to where swap was, where's swap? Swap, right? Well, there's actually destruction here, 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 and here. So it might seem like, well, swap, that's less work. Yeah, but it actually maybe kind of does more harm in certain situations. Just think about what it's doing and use your intuition. Inversion mutation, okay? So any questions about the permutation things? Again, did anyone like invent their own genetic operator for the permutation representation? Or did you invent your own and then discover that it was already a thing like inversion mutation? That's fine. I was just curious if anyone did. It is a tricky one, right? I think, didn't John say he did something? He kind of did like endpoint swap, I think he said, where he picked like, instead of 2 points to swap, he picked multiple ones and then just shuffled them in the, I guess it's kind of different. Yeah. Anyways, okay, genetic operators for floating point real representations. Now, I've said this before, a lot of the variations, or several of the variations of evolutionary computation are specifically designed for real number things. But in the context of a GA, you could still use one. All right, various values. Yeah, so when I say real numbers, they're floating points because, okay, we are bound by like the computer's limitations, right? But the idea is they're continuous values. There are a lot of complex genetic operators for this, so I'm only going to cover a few of the simple ones. But in practice, there are other forms of evolutionary computation that are perhaps better, that are designed to work with this type of representation. So a crossover. There are two broad ideas where you've got like a discrete and like this intermediate one. So the discrete idea is like everything we've seen before has been like a discrete crossover, where this intermediate one is like maybe you'll kind of have points between the parents. You won't actually have a copy of anything from the parents, but you'll have like points in between the parents. So here is a single arithmetic crossover. So I pick one point, select an index at random, okay? Average the values between them. You see what I mean? I didn't take the 0.8 and the 0.2 and swap them. That would have been a discrete one, okay? And that'd be fine. You could do that. But see here is I took it and I got like an average, like a point between them, okay? Do you see? It's kind of neat because it kind of breaks the almost like the rules, for lack of a better term, with crossover, where like you exchange information from the parents. Where here, yes, there is still an exchange of information because information from the other parent like affected it, but it wasn't like a discrete copy, which is pretty neat, I think. Simple, same idea, but you know, for a chunk. Whole, you do the whole thing, though that, you know, that would make sense in certain situations. So like, don't think like, oh, you should like that would be obviously quite destructive. Mutation, select an index and replace the value at the selected index with a value from a continuous uniform distribution within some range. This is a fancy way of, if the stats stuff spooks you, don't worry. This just means like, if you allow numbers between 0 and 1, pick an index and then pull with equal likelihood any number from 0 to 1. Okay, you see what I mean? That would be uniform. Uniform, all it means in this context is I'm equally likely to pick any possible number from the allowable set of numbers to replace it with. Okay? Happy, sad? Yeah? Then there's, yes?
I have a question about the whole arithmetic crossover.
Yeah.
Like, you're only getting one unique child, right?
Well, you ended up with 2 copies of them.
Yeah.
So, yeah, that's interesting, isn't it? So you end up having like 2 versions of it, but then like, depending on how you're implementing these things, like if we end up having 2 versions of it, think about like what that could mean. Like next time there's a crossover, and this one might get crossed over with someone else, and this might get crossed over with someone else. It's still, they're gonna like diverge really quickly as well. You could think, like, imagine this is, like, I'm searching for a point in a high dimension, like 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm looking, like, this could represent some point in a 9-dimensional space, right? I mean, it does, right? But, like, you could think of it like that, and imagine, like, we are actually looking for a point in this 9-dimensional space, right? And then something like this is like, well, this was a good spot, this was a good spot. Maybe the spot between them is good. So that's the idea, right? They both kind of move towards each other. You can think of it like marbles, right? Where, yeah, they have some amount of like attraction to one another. Again, you could look at this and be like, okay, do it and then add noise. Sure, you can do whatever the hell you want. When we talk about something called particle swarm optimization, you'll kind of see how that kind of takes these ideas, but in a less obviously a genetic algorithm-y type way, but it totally still kind of is if you think about it. You'll see. So mutations, and then a Gaussian. So this would be like, okay, so maybe you don't pick numbers from a uniform distribution, like equally likely. Maybe some are more likely than others, okay? So, like, yes, I can pick any number between 0 and 1, but I'm more likely to pick numbers around 0.5 than I am a number around 0.9. Why would you do that? Depends on what you're doing, right? This is just a general idea. You only use these tools when you need them. A lot of these are fairly esoteric tools that you only need them when you need them. And then self-adaptive mutation, a non-uniform mutation, but the value of the variance is part of the chromosome. Yeah, this one's actually pretty neat. I'm only showing it to you, not as like this is necessarily a particularly important one, but here's a crazy idea, right? Like when you pick a normal distribution, there's some like parameters for it, right? depending on what mu is, like depending on what the standard deviation is in the median, or mean, pardon me, you'll get different distributions, right? The shape, like here's 4, 1, 2, 3, 4 different distributions, okay? With different parameters, right? This one's -2, right? Its center. The other ones have a center around 0, but depending on like those values, you get different shapes, right? So, if looking at the blue one, I'm very likely to pick a point around 0, but not so much around point -1 and certainly not around -2. You see what I mean? Now, what should these be? You know, you can pick them. What if you added those two values? What if you just added those, like you stuck those two values on to the end of the chromosome, like here. And they are subject to mutation and crossover as well. Meaning that the values for these are also changing. And it ends up being something that is also optimized through its own search, which is pretty interesting, right? It becomes very like self-referential, which is always very interesting, I think. Cool, eh? Yeah, I think that's pretty neat. All right, tree representations. So tree representations are like typically your traditional genetic programming. Genetic programming, it's just a GA, but you're evolving like functions, okay? Whether it's a mathematical function or a programmatical function, whatever. More on GP later. But tree representations are like the classic representation for genetic programming. We talked about this before, right, when talking about representations. Yeah, okay, genetic operators can become tricky when working with typed genetic programming. More on that in a moment. So, crossover. Here is a basic one. Pick some subtree. In each parent, swap them. There. It's like 1-point crossover, but for a tree. So imagine these are two expressions. And by the way, if you don't remember, let's just like make sure how we can go from the tree to what it means, right? So we've got like 2 pi plus x plus 3 minus y divided by 6, I guess. I simplified it, okay? That happens a lot in genetic programming. So, like you will see like giant ass trees. There's this idea of bloat that we'll talk about, but you get these giant ass trees. And it's a funny thing, like how many trees are there that represent just like the number 4? Right? Well, we can have like a single node 4, or you can have like a plus 2 and a 2. We could have a multiply a 2 and a 2. Oh, we can have a 1 plus a 3, right? Or we could have a plus 6 minus 2. Uh-oh, there's literally an infinite number of trees that can represent even just a single value, right? So there's a bit of like a conundrum where like, okay, in this case, there is one smallest way to represent the number 4. It is a single node containing the value 4, okay? Everything else is crazy. So if you were to expect, you've got this like literally infinite search space, and there's one point in that search space which is like the smallest version of that tree, how likely are you to find the smallest version of the number 4? Not very likely, right? Unless you had some selection pressure to like small trees, but we're getting ahead of ourselves, okay? Just food for thought. Anyways. And this would be like 3a times 3 plus y plus 12, and you can simplify these trees. But the point here is you would just take this subtree, put it there, take that subtree, put it there. See? Boop, boop. Now, by the way, you have to be careful. Like, there's a big question. Like, well, should you have like tree simplification with like built into your algorithm? Maybe. Now, that's a very hard problem. Good luck figuring that one out. But like when it's something like this, I could have picked the subtree, right? If I were to place it with the number 6, like I could select this subtree, it's the leaf, sure, and swap it with like this, right? Well, that's a hell of a lot different than the number 6, you know? So, you know, you win, you lose. And then mutation. Pick a subtree and then replace it with some other subtree. Here, I replaced it with the subtree, which was just a single node, a single value there, a constant or a variable y. But that's the idea. Now, how do you generate those? Well, you generate them however you want, randomly, whatever. That's like an initialization idea for genetic programming, which we'll talk about later. Any questions about the GP crossovers? Okay. This list is in no way exhaustive, nor should you even assume that things on here are going to be good for what you're doing. Like everything, like if it hasn't been obvious, I'm encouraging creativity. Try whatever the hell you want to do, see what works, see what doesn't work. That's the fun of it, right? And you always have something to talk about, right? Think about your projects. You're like, well, I tried this crossover because I thought it would work. Turns out it sucked. So we tried this. There's a story there. And like when you say, here, turns out it sucked, and it's like, well, why do you think it sucked? And there's a discussion there. You don't have to know. It just use your gut. Like, what's your gut say? It's a very empirical world when doing this type of stuff, meaning like coming up with like concrete like theorems and facts about what's going on is very challenging. So a lot of it comes down to like anecdotes, but like well reinforced anecdotes with empirical data, but like it's like I can't prove this, but this is what I think. That's normal, and that's part of the fun of it, right? You've got the flexibility to just try and explore and come up with ideas. Okay, the word destructive was used above when referring to genetic operators. It's not particularly well defined. I warned about this as we were going, right? But it's used to kind of communicate this idea of like how much the information with the chromosome is getting changed. And how destructive something is will also depend on the representation and the problem. Like if the contiguousness is what's important, then changing like the contiguousness of those that's where the destruction is going to be. If the contiguousness actually isn't really important, then maybe some crossovers are not as disruptive, depending on what it means, depending on what that genotype to phenotype relationship is. For example, a single point crossover on an integer representation for a robot navigating a maze. On average, it changes half the chromosome, but the information in the chromosome is preserved and transformed. Okay, the part of the chromosome that is transferred represents a subpath that will move to the other chromosome. It's not particularly destructive. There's like one point where it like gets really mixed up. But on the other hand, a uniform crossover on the same problem can be quite disruptive because it's like that contiguousness, the order of the steps for the robot navigating a maze is going to matter quite a bit. And then exploration versus exploitation. Consider the following population for GA maximizing the integer value. We saw this before. With this, without mutation, like we could just do crossover, any of the crossovers we looked at, we could never find the optimal solution. Why? Because we can never get a 1 in this index, right? So we're in trouble. So no matter how much the search exploits what it already knows is good. Let's say like, okay, it thinks these are pretty good, right? So let's exploit that, okay? We have no way to get it to jump anywhere else based on just like exploiting. Now, exploration and exploitation are kind of used almost like interchangeably to mean two different things, but it's a weird thing where depending on who you talk to, they'll be like, no, that would be exploration, or that's exploitation. They are two concepts, and thinking of them as like a one or nothing is also a bit of a mistake in my opinion. So I'm just giving you these ideas. Yeah, exploit in this context means making use of what is already known to be good. Because of this, it's not possible to find the solution with a single point crossover alone. That's where flip bit or bit flip came in. It gave us a new way to add information, okay? It gave us a new way to explore the search space. Now, someone would argue like, no, mutation is exploitation because you take an individual chromosome and you modify it. So you take what's already good and then you modify it. But the idea of like exploration is also tied to like destructiveness, where you could have a crossover, where here I'm using the word exploitive in the context of crossover, right? Like we're exploiting what's already good, but we have no way of getting there, you know? But depending on the crossover, if you have a very destructive crossover, and it's going to change the chromosomes, the children, a lot, you can make an argument, well, that's very explorative because it's going to throw these things into way other parts of the search space. So you just be careful how you're using the words. Just use them with intentionality and describe what you mean effectively, and you'll be fine. All right, this is destructive. Okay, thus sometimes a destructive operator is very beneficial. Further, consider a population that has converged on some local optimum. No matter how much the information local optimum is exploited, you can't get out of it. By increasing the exploration, perhaps the search can work itself out. Okay? And yeah, crossover is not always exploitive, nor is mutation always explorative. Like I was just saying, it's kind of like every individual situation, genetic operator, encode, like representation, all kind of play into each other on this. So any questions about that? All right. Selection and population management. So some of this is going to be review. Any questions before we start this topic? Okay. Okay, one of the main, okay. So we have a population, and like, yes, individuals are changing, but it's often nice to think about how a population is changing over time, like in aggregate. There's obviously still value in thinking of individuals, like you're looking for some optimal, right? So it's going to be one. But the population's evolving because traits get passed around populations. So the population itself often has a fixed size. It doesn't have to. You can have genetic algorithms that have a growing population. And maybe there's like culling events or something. I don't know, but you can do whatever you want. But often a simple GA is going to have a fixed population size. And that fixed size is part of like, that's basically it's the analogy to like what purpose does it serve? Like what force does this add to the search? It's the constraint. It's the limited resource that necessarily causes some form of competition to exist with selection pressure, okay? So they are somehow, every chromosome is competing for a seat in that population, but there's a limited number of seats, okay? Yeah, okay, so when we have a population, we have to have a way of, okay, who gets to stay in these seats? So that's where our selection strategy comes in. This determines an individual's ability to survive and have offspring based on their fitness value. But you'll remember when we talked about selection, it wasn't things like always pick the top whatever, right? You do something like that, that's not selection. You don't have a GA, you've got a weird random search. And selection is always relative to everyone else in the population. So they're competing with each other while also having to kind of like if the whole population is evolving, there's some amount of like cooperation there because like, well, they have to like mate and whatnot, but they're also competing. And the selection strategy is independent from the problem being solved. I don't care what problem I'm solving, I can do tournament selection, let's say. So before even that, we talked about this before, there's like generational and steady state. For the most part, everything that I've shown you has been a very generational style GA, genetic algorithm, where you've got these very discrete generations. The code example I showed you was generational. It was, okay, evaluate the whole population, select who's going to make it to the next one, apply the variation operators, that's the population, repeat, right? There was a very discrete time step. with this, so what, okay, a whole population is created based on current population, new population becomes the current one, the population size remains the same, and there is a very discrete transition between generational. With a generational algorithm, depending on how genetic operators are applied, the new population is filled with copies of unchanged selected chromosomes and mutated selected chromosomes and offspring from crossover, right? That's the idea. But you could have a steady state one where like with a generational, right? So let's say I have like a parent and a parent, right? And then let's say, okay, there's crossover, and then, I don't know, let's make them different. This person has hair, and this person has big hands, right? Maybe after crossover, this person has half hair and one big hand, right? And this person has the other half of the hair and a big hand or something, right? So you get the idea. There's some crossover took place, right? But then there's like another one here. Some, you know, it's a full population, right? This is the population. This is like the next generation, but it's not the population yet. This is getting filled to become the population, right? Once these are created, these can't mate with them, at least not yet, right? They are not candidates for selection this go around, okay? But in steady state, what you do is I don't have another color. I'm trying to think of the best way to do this. Do I have pictures here maybe? No, I don't, sadly. So big feet, hair, they need glasses. Now this is not going to work at all. Here's the idea, right? I've got a population. All I'm going to do is I'm going to pick two, mix them up a bit, and put those two in to the same population. Repeat. So there's no like next generation, it's always the same population. But with this comes something else. This steady state is like a generalization of the discrete one, but I'll explain that in a second. But okay, with this, every like offspring can then be a candidate immediately for another like crossover mutation. Okay? Yeah, happy, sad? So there's no discrete transition between generations. With steady state, given a single population size of mu, these are commonly used in like formal writing in evolutionary computation. Like mu is the population size, but in general, people are using whatever the hell they want. Select some number of chromosomes, lambda, and apply the variation operators to produce the offspring. Replace lambda crossovers in the population with the offspring. The generational gap is the proportion of the population that was replaced, lambda over mu, okay? So if I pick 2 and my population is size 100, it's 2 over 100. That's the generational gap. If the number of chromosomes selected is equal to the population size, it is equivalent to a generational algorithm, meaning if I select everybody and then replace them all, it's generational. If its gap is 1, it's generational. Do you see? Okay, that's the idea. If you like generational, awesome. If you like steady state, cool, more power to you. It doesn't really matter. It's the same idea. They're both going to work. Yeah, with the generational algorithm, the whole population is replaced. But with the generational gap less than 1, there needs to be an actual other selection strategy that we haven't really had to consider. What that is, do I have? I'm checking here if I've got an example. Okay, I don't, which is frustrating. I thought I had a figure for this. So when it's generational, I've selected everybody I want they all get a seat in the next one. I've got mu empty seats for them, right? Because I've selected them. They're going to be the new population. Fine. But when I have like, if I do the simplest one where I pick 2, mix them together and pull them apart, if I have a fixed population size, look, I copy these 2 and I change them to make children, right? I can't just add them to the population because then I'll have a population size of mu plus 2. So I have to pick 2, in this case the lambda. I have to pick lambda elements in here to replace. Now in generational, when lambda is equal to mu, I replace them all. There's really no strategy there other than they're all gone, replace them all. Doesn't matter. But now I have to pick mu, or lambda, some number to replace, in this case 2. Who do I replace and how do I pick them? Do I replace the 2 that I copied? Maybe, maybe not. Maybe I go here and pick the 2 ones with like the worst fitness. I could do that. Maybe I go here and I pick the ones that have been changed, have remained unchanged the longest, like the oldest members of the population. Maybe I do it where it's random, where I just randomly pick. Maybe I do some like diversity measure of some way, although diversity is often quite difficult to measure quantitatively. But maybe some diversity metric where I pick some that will add way more diversity, where basically this chromosome and this chromosome look really different. So let's replace that one because it's really different. However we do it, it's a new selection strategy that we have to consider when doing the steady state. That we don't with generational, because like we've got this like implicit one where, well, we're replacing them all. So how do I pick them? Just pick them all. Tournament selection. There are 2, yes?
Are there any, like, problems with doing that steady state thing? Like, I'm thinking of, like, inbreeding or, you know.
That could still happen with the genetic, that could still happen really easily with generational. In terms of like general problem, I'm not really familiar with any just general problems with it, with a sufficiently large population at least. Yeah, nothing particularly wrong with it. It becomes harder to like maybe do some like, it's not that it's overly difficult, but to me, it's really easy to say, okay, after 1,000 generations, okay, I know what that means, right? But there's no generations here. So like, how do I, So often what people will do is they'll measure like mating events, okay? Where, okay, after some number of mating events, but like, you could do that measurement with a generational one too, where the number of mating events can vary wildly different though, between, because it's kind of like depending on like crossover, right? So, you know, counting generations versus counting some, like I could have 1 billion mating events happen in 1,000 generations depending on the population size, or 1 billion in 1 billion generations, right? So like generations are a little bit more like concrete for me to follow, where the mating events is a lot more like hard to put your finger on. So we can still understand what it means, but in terms of like thinking of it like as a nice measurement, I always have a little bit more difficulty there. Not that it's impossible, right? Like I'm sure we all kind of wrap our head around it, but I don't know, generations are very easy for me, I think. Yeah. And I don't know, I always do the generational approach. I just find it so much simpler and like cleaner and much more like programmatic, like, I don't know. But there's nothing wrong with the other one. Okay, tournament selection. 2 very basic selections can be used. So uniform selection. Each chromosome has an equal chance of being selected, okay? Where PI is the probability of an individual chromosome being selected, right? 1 over mu, where mu is the population size, okay? Some forms of evolutionary computation use this selection exclusively. One where like you literally just pick them at random. And there's like almost like no selection pressure built into the selection, but it's built into other mechanisms, but we're not going to cover them. I think maybe even differential evolution, I can't quite remember. However, in general, it's not going to perform really well as there's no, like, if you did something like this with a GA, it's not going to work really well, right? There's like no selection pressure, okay? I pick one, like I could get unlucky and pick the worst candidate solution every time. Do you see what I mean? I know this, okay, let me take a step back. This section is called tournament selection. Right now though, I'm not talking about tournament selection. I'm talking about uniform selection. I have an equal probability to select any candidate solution, okay? Yeah, there's low, effectively zero selection pressure. The other, okay, another one, a broad one, is select the top chromosomes only and apply the genetic operators. Well, this is way too much selection pressure, okay? We've already kind of seen it. This will not perform well as the population will converge way too quickly, and there's just way too high selection pressure. So you need to find somewhere in the middle. We talked about this, right? Where it's like, okay, randomly pick, because remember like with tournament selection where it was like pick K, right? Well, if it's 1, you've got no selection pressure. If it's K, you've got way too much. You're always picking the best one. So K is that dial. So right now I'm talking about the two extremes. Yeah. So the alternative and highly effective solution is to go somewhere in between. In fact, typically you go not really in between, but you go way closer to the select 1 side, where you pick some K where K is often a relatively small number, like 2 or 3. All right? So here I pick 3 with equal probability, but then of those 3, I take the best one. Right? So why did I take A? Well, it had a 5 because E had a 2 and T had a 2. But R had a 6. And look, there's bigger ones that didn't get selected right now. But right now, I'm picking A. There. Okay, I've selected 1. Now I'm going to do this repeatedly. I'm going to do this like mu times if I'm doing generational, right? Right? Mu time where mu is this population size to select them all for the next generation. Okay? You see, that's tournament. And yeah, I know I said pick somewhere in between. Yeah, although 3 is between like 1 and mu. But like if the population size is like 100, for example, you're going to still be picking something like a 2 or a 3 usually. I mean, pick whatever works the best, but that's often what you're going to see. Clear? Now, what's neat about this one is it's all relative to each other, and like they all have like an equal chance, okay? Yeah, okay, if K is 1, it's the same as uniform. If it's mu, it's the same as always selecting the press, so as K increases, so does selection pressure. So, okay, there's our tournament, and then the other one is gonna be like a fitness proportional selection. This is where like roulette wheel comes in. So there are a collection of these where the probability of selecting an individual depends on the fitness value compared to the whole population's fitness. So what you do is, here's just the fancy math. Okay, the simplest of these is to have a probability be the individual's proportion of the total population fitness, right? So let's say the total population fitness is 100, right? Like if you looked at all members of the population and you add up all their fitness values, that's what that is, okay? So let's say it totals to 100, right? I take the individual, and maybe one individual candidate solution has a population, or has a fitness of like 7, okay? So that is 7% of, like 7% of the total population came from that individual. So it has a 7% chance to be selected. That's the idea. Where maybe another candidate solution has a fitness of 1. It has a 1% chance to be picked. It can still be picked, but it's not that likely. So the benefit here is selecting highly fit individuals. The search may produce high quality results, but of course it might converge too quickly, right? It might get stuck in a local optimum. Where tournament selection, you had that K to be a dial, where this, not so much. Although in practice it works fine, it works really well, right? But it works in a different way. Do you kind of see how it's like a very different category? Where before, like okay, we randomly picked and then just take the best one, where this one is like, well, I'm going to pick ones, and my likelihood to pick them, my probability to pick them is going to be based on its actual fitness value. Further population begins to converge. Okay, it's going to stagnate with the value. Oh, yes, this also becomes a big problem. I think I have an example of this later. Get stuck in local optimum. Yeah, when the population begins to converge, where they're all very similar, all of their fitness values are going to be very similar, and now you have no like selection pressure to goodness, right? They all have the equal likelihood of being picked. So you kind of like lose its whole value. But like modifications include like adding some constant stuff, they call it windowing. We go through examples. Several selection probabilities are shown below table. Okay, perfect, right? So do I have a picture? Yeah, so here. We'll go back up to the tables, but the idea is this. Imagine I have 1, 2, 3, 4, I have 6 chromosomes, okay? If I add up their total fitness value, do I have it here? Okay, I don't know what their total fitness value is. Okay, we could calculate it by adding these numbers up. Doesn't really matter. But A takes up 8.2 of the total, which is this proportion. We think of this as like a roulette wheel. You know, roulette. Raise your hand if you don't know what roulette is. Be honest. It's okay. Okay. So. Or like that, you know, spin the wheel, you know, right, and it lands where you go, right? If you're playing the Price is Right and you're spinning the big wheel, right, each number has an equal likelihood of being selected, right? Now here, though, imagine that, yeah, they actually aren't the same size. The size is proportional to their fitness. You see? That's the idea, okay? So with this, you then like spin the wheel, and wherever it lands, that's what you pick. You're more likely, you can pick any of them. You could land on any of these things. But by virtue of having a bigger chunk of the pie, it's more likely going to pick A. But it can still pick the other things. That's the idea. All right, so yeah. So if A, B, and C, total population, if these are, this is their proportions, you see, right? But if you add some constant, you can like really modify what the probabilities are going to be. So if you want to like somehow tune it a little bit. And then windowing is, I can't remember, like, do I say what windowing is? I can't remember even what it is, even just by looking at this. Oh, it ranks them. It's like, okay, this is the best one, so it gets 2/3, 1/3, 0/3. If there was more, you would do like, okay, 5 6s, and so on and so on. You know? Yeah, okay. And then rank, same idea, you just rank them though. Yeah, okay, that would be like with windowing, right? Same idea. Okay, cool. Long story short, it gets us to this general idea, and all of the different like math that we were doing, which you can tinker with all you want. I'm not going to go over all the possible effects. You just play with it. You can run the numbers yourself. All of that tinkering by adding some constants, doing windowing and whatnot, are just a way to like modify the shape of the size of these pies. But the idea still remains: the size of the pies are directly related, are directly tied to their fitness values, okay? Where tournament's a little easier. I do have an implementation of this. But, okay, yeah. So typically roulette wheel has one arm and is spun mu times. An alternative is to spin the roulette wheel with mu arms once. This means that you only spin the wheel once, which is kind of interesting. And it produces a nice diverse set, right? So, So imagine I had like 4. I needed to select like 1. Okay, imagine I had 6 points around here is basically the idea, right? Instead of like spinning it 6 times, you have 6 points, and then you spin it once. And then you go like, okay, where each point is, that's what I select. You can do it that way too, which has some interesting properties, which is kind of nice. Yeah. Although possible, fitness proportion selection often requires some alterations to work with algorithms. Yes, this is another problem too, is it can get hairy for minimization problems, the math. You can make it fit, right? But the intuition gets a little tricky. When you have maximization problems, it's not too bad, but with minimization problems, doing like the fitness proportional can kind of get kind of wonky. Yeah. Yeah, and I guess there's a good place to end. That's survivor selection. Any questions though, before we wrap up? Okie dokie. I'll see you later.